Now we're going to talk a little bit about gases. And gases is one of those phases of matter which we're pretty much not that familiar with, mostly because we just don't see gases. But we certainly feel them. I mean, wave your arms and hands around and you can certainly feel it. Whenever the wind is blowing, you're feeling the gases. But gases are always around us. Our atmosphere is always present. So let's talk a little bit about gases and how we describe them. The way we describe gases in chemistry is through a theory called the kinetic molecular theory. The kinetic molecular theory has some postulates or some assumptions that we make about gases, and all of them are fairly true. So the first one is that gases travel as individual molecules. And what that basically means is that as gases are constantly, the molecules are constantly moving around. And they're moving around by themselves. They're not kind of attracted to each other. Which brings me down to the next thing, is that there is very little interaction between gases. When gases do interact, they kind of just bounce off of each other. You know how if you take a ball and you throw it up against the wall, it just easily bounces back? Well, that's kind of what gases do. When gases hit each other, they just bounce off of each other. When gases hit the sides of a container, they're just bouncing off the sides of the container. They interact with each other very little bit. Also, gases are really far apart from each other. I mean, they're compared to a solid and a liquid. Solids and liquids, the molecules are really, really close. But for gases, they are relatively far away from each other. And so that kind of also helps to show that the gases themselves are independent of each other. And they act as individual entities, individual molecules or atoms. Also, gases, when they're moving around randomly. There's no kind of predicted pattern as to how individual molecules or atoms of gases move. They're just constantly moving in whatever form or fashion that they want to, bouncing off of each other, bouncing off the walls, and they are moving extremely fast. So fast that at room temperature, the gases in this room, the molecules are moving almost 1,000 miles per hour. I mean, that's just crazy fast. So that all of those postulates encompass what we call the kinetic molecular theory of gases. Now, we can kind of take this theory and make mathematical models about gases. And to do that, we have to look at certain properties of gases. And we're going to really focus on three major properties of gases. And that is the pressure, the volume, and the temperature. So first, let's talk about pressure. Pressure, what is pressure? Well, pressure scientifically in physics is the force per area. It's the amount of force something has over a certain amount of area. So if you take, for example, like this pen right here, and I'm like poking my hand right here, that doesn't really hurt. But if I did it with the other side, that's a little bit more painful. So that's because this area right here is a much smaller area. And I'm applying a force, and force divided by area divided by a small value, you get a large value. So I'm getting more pressure because it's less area. So pressure is a force that something is applying a force to a specific amount of area. And the units of pressure in the SI units for pressure is a new unit that you're probably not familiar with, and it's called a Pascal. And a more common unit that you are more familiar with is probably pounds per square inch, or PSI. For example, when you're blowing up your tire, your bike tire or your car tire, usually it's between 30 and 35 PSI, which stands for pounds per square inch. So that means there's 30 to 35 pounds. So think about what 30 pounds of potatoes or a 30-pound bag of sand, how much that is. A small child weighs 30 pounds. So that 30 pounds is on 1 square inch. So think about how big a square inch is. So that's an inch by an inch, a square. And so there's 30 pounds of force, 30 pounds pushing on every square inch. That's the amount of pressure that's inside that tire. In fact, that's actually, it's really, in the tire, for example, it's 30 psi above the atmosphere, above whatever the air is that you're in. So That's because we have to think about our atmosphere as gas pushing down on us, which brings us to another type of unit that we have for gases, and that is atmosphere. So when we are at sea level, we think of the sea level that there's one atmosphere of gases above us. And so that's defined to be one atmosphere. A lot of gases, the standard gas pressure is one atmosphere, meaning it's at sea level. Another common unit that you see about with pressure is, besides atmosphere, psi, and Pascal, is a unit called millimeters of mercury. And that comes from a barometer. And the barometer was invented by a guy named Torricelli, and that actually is another unit that we have for gases, is torr. So before I get into barometers, let's kind of back up here. We have lots and lots of units for pressure. We have Pascal, we have torr, we have millimeters of mercury, we have psi, we have atmospheres. There's all kinds of units that we have for pressure. Just like we have all kinds of different units for length. I mean, for length you got miles and inches and centimeters and meters, yards. So there's lots of different units for pressure, just like there's lots of different units for other properties that you're familiar with. Now let's go back to the barometer. The barometer is a way we measure pressure. And initially, the barometer was made out of a tube. And it was usually it was like water or some other liquid. And the liquid that was most generally used is mercury. Today we don't generally use mercury thermometers because mercury is a very toxic metal. And so we try not to have lots of toxic materials around us. So mercury kind of isn't used much. But back when barometers were first being developed and used, they would have a pan of mercury and kind of take a tube, and what they did is they filled that tube up completely with mercury and they inverted the tube. Now when you invert the tube, what's going to happen is the liquid inside of that's going to leave that tube, and it's going to create a vacuum above it, above that liquid. And so there's not going to be anything in there above the liquid. And you're just going to have this column of liquid and this pan of liquid on the bottom. And so what would happen is, as you increase the pressure, you're increasing the pressure on that pan of liquid. It's going to cause that liquid to go up that tube. And if you decrease the pressure, the liquid will go down the tube. And so you can measure that level of liquid, in this case of mercury, and determine what the pressure is. And that's where we get the term millimeters of mercury. Millimeters of mercury being how high a tube of mercury was above that pan of mercury. And so that ends up being a unit of pressure. And the guy who developed or invented the barometer was a guy named Torricelli, and that's where we get the unit torr from, to honor him. Now, like I said, we don't use mercury barometers anymore. Instead, we have what we call aneroid barometers, which kind of use a spring inside and some metal plates. And so as the pressure of the atmosphere changes, it pushes on those plates, which compresses that spring. And that compression then is related to a dial, a needle. And so we can then measure, and that needle is on a scale, and we can actually measure the pressure in that way. And so that's using an aneroid barometers, which is what we have today. Your smartphone actually has a barometer built into it, because GPS systems have to use pressure to help as part of the process of GPS. And so your phone itself actually has a built-in barometer in it. And you can download an app to determine what the pressure is in your current location if you want. Pressure is basically the force of the gases that are being pushed on. And in the case of gases, let's think of about a balloon. When the gases are inside the balloon, those gas molecules are bouncing around all over the place and is keeping the balloon inflated. And so pressure is a very important property of gases. The other two properties that I mentioned earlier, volume and temperature, are also important. I mean, volume we've kind of talked about previously. Volume is the amount of space something takes up. And so gases do take up space. They take up the entire space of whatever container you're holding or that they're contained in. And so volume plays a role in kind of mathematically determining the properties of gases. And the last thing is temperature. Now, temperature scientifically is not how hot or cold something is. When we look at on the molecular level or the atomic level of temperature, temperature is related to the kinetic energy of the molecules or atoms. Those molecules or atoms are moving around. So that means they have kinetic energy. And that kinetic energy is related to the temperature. The higher the kinetic energy, meaning the faster they're moving, the higher the temperature is going to be. And so hopefully you can see how that relates to gases. As those gas molecules are moving around, if they're moving around really fast, the temperature is going to go up. If they're moving down slower, the temperature is going to go down. So there are many ways to relate these variables of pressure, volume, and temperature. And so we have mathematical explanations, constructs, to help us kind of relate how these properties are to each other. The first one I want to talk about is Boyle's law. Boyle's law is a mathematical equation that deals with the pressure and the volume. So let's intuitively think about what happens if we have a container and we keep everything constant. We keep the amount of gas inside that container the same. We keep the temperature the same. And the only thing we're going to look at is the pressure and the volume. So remember, pressure is the force that those molecules are hitting the side of a container. So if we take that container and we compress that container, so we make the volume smaller, what's going to happen to the pressure? The volume decreases, the pressure is going to go up. And so that means that they are inversely related to each other. When something is inversely related, that means as one goes up, the other one goes down. So Boyle's law tells us that as the pressure goes up, the volume must go down. Or as the pressure goes down, the volume has to go up. And so that's Boyle's law. The other law relates the volume and the temperature. And so volume, let's think about how those two things are related to each other. If we increase the temperature of something, what is temperature? Temperature is related to the kinetic energy of a material. So if you increase the temperature, that means you're making that energy of those molecules faster. Those molecules are moving around much, much faster. So that means they're going to hit the sides of the container more. So we're going to keep the pressure the same though. So we only want to see how the volume and the temperature is related to each other. So we have to keep the pressure the same. So by keeping the pressure the same and we increase the temperature, the volume has to increase to keep the pressure the same. And that's because as the temperature goes up, those molecules are moving around much faster, and so that's going to hit the walls more, which is going to increase the temperature, but it's going to increase the pressure, and so as that pressure increases, we want to keep that the same. So to account for that, we have to increase the volume. And so as the temperature goes up, the volume also goes up. That means they are directly proportional to each other. Since they are directly proportional to each other, as one goes up, the other one must go up. Or as one goes down, the other one goes down. So temperature and volume are directly proportional to each other, and that is what we call Charlet's law. In English or in American, you might say Charles' law, but he was a Frenchman, and so it's actually pronounced Charlet. So Charlet's law says that as the temperature increases, the volume goes up. The third law I alluded to when I was talking about Charlet's law, and that is Gay-Lussac's law. And his law relates to pressure and temperature. So just like what we were talking about earlier, as the temperature goes up, it's got to increase the pressure of the container. And we're going to keep the volume the same. And so we keep the volume the same, then the pressure's got to increase. So that says that as the pressure goes up, the temperature goes up, or as the temperature goes up, the pressure has to go up. Or vice versa, the temperature goes down, then the pressure's got to go down. And so again, those are directly related to each other, and that is Gay-Lussac's law. And so those are the three main laws that we've talked about. Boyle's law, Charlet's law, Gay-Lussac's law. that kind of relates these three properties of gases. These laws really only apply if we are in an ideal world. And for the most part, gases are what we term ideal gases, meaning that they obey the kinetic molecular theory, that they don't interact with each other, that they have a very small volume, that they are constantly bouncing off of each other, and there's very little interaction, like I said. However, in real life, that's really not the case. The molecules and the atoms do have a volume, and they do interact with each other. But in real life, when those interactions, when they do occur, they occur at specific or extreme temperatures and pressure. And so at room temperature, we can pretty much say almost all gases are ideal gases. And so they follow these laws that we've laid out pretty closely. It's only when we get to the extremes of these pressures and temperatures when we have to really think about those molecules and those atoms being real, and that they really do have a volume and that they really do interact with each other. But for the most part, at room temperature, where most experiments are done, everything is an ideal gas.